Okay, so chapter 4 of this book is called Theory. Theory of climate. The biggest thing is to understand the forcing, where the energy for the system is coming from. Why do we need energy? Basically because we are moving things, right? We are creating winds, we are moving clouds, we are moving water, we are dragging the ocean around, creating circulation in the ocean, we are building glaciers, we are melting glaciers. All this takes energy, and energy is typically looked at as a budget. So any given quantity X, you can think of it as heat, as water vapor, as a gas, anything, or something that's dissolved in the water, and the partial derivative of that quantity X in time is equal to the inputs, whatever are the sources. So if energy is coming from the sun, that's an input. Output, or the sink, is what is being sent back to space. So energy is coming in, energy is going out. If they are equal, then this side will be zero, then your quantity X doesn't change in time. Right? There are lots of details. If you have had enough math already, then you know that when we say partial x partial t, that means x is a function of multiple variables and time is just one of them. Typically when we don't have a continuous measurement, let's say, of something, or it's a very complicated function, then we cannot solve it analytically. Then we tend to write it numerically as delta x over delta t equal to I minus 0. So at any given point, you have x at time 1, x at time 2. You can take their difference and divide by t and see what is coming in and what is going out. It could be like a river flow, for example. There is a river water that is being due to, let's say, rainfall falling, and catchment is collecting the rain, putting into the river, and the river is flowing out, and so on and so forth. Okay, so just get a sense for this kind of thing. So here is an illustration of a budget equation. We have input, we have output. We are looking at the balance of delta x over time delta t as what is input and what is output. A box containing the conserved quantity x that does not include internal sources and sinks will change in time according to the external inputs minus external outputs. So this is kind of the reservoir size. So if it's in equilibrium, then the amount inside doesn't change, let's say the CO2 in the atmosphere or in the ocean. So just try to get a sense of that. When we say internal sources and sinks, you can think of atmospheric CO2 that has been put together, let's say by burning fossil fuels and what is there from the beginning. Internal source is like a volcano going off and putting CO2 into the atmosphere. So if you are thinking of human input and what is being taken up by plants and by the ocean, then volcanoes will add an internal source, or there could be an internal sink as well of some sort. Okay, so you can also write delta x over delta t as x2 minus x1 divided by t2 minus t1, in which case you can write x2 equals x1 at time t0, let's say, plus input minus output times delta t. So you can do many simple calculations for this. If you're starting at the beginning of the Industrial Revolution, x1, let's say, would be your concentration of atmospheric CO2, which was at 280 ppm. Then over time, let's say through the 20th century, we have put in a lot of CO2 as input by fossil fuel burning, and whatever is being taken up by land, ocean, and what remains in the atmosphere is the output, and that's the time over which it's changing. That should give us the value of CO2 at the end of the 20th century, for example. Okay, the other most important thing to deal with here when we want to think about climate is the energy. So this is a Planck constant times the nu is a frequency, so that is Planck's constant times the velocity of speed of light divided by the wavelength. We are not going to get into wave particle duality and so on and so forth, but speed of light is basically frequency times the wavelength. Here it tells you briefly that wavelength can determine the energy content of the radiation we are going to look at. So short wavelengths, E will be higher. Longer wavelengths, E will be lower. Immediately you must think, what is the energy coming from the sun considered as? It is considered short wavelength, and the energy going from the earth to space is long wavelength. So you also refer to it as short wave radiation and long wave radiation, because radiation is the energy. Long wave, you can, or infrared, you can think of it as what our body emits, for example. Because we have a warm body, our body is constantly emitting infrared, but we cannot see it because our eyes have evolved only to see in the visible light, whereas many animals which hunt at night, including some cats, birds, owls, lions, whoever, can also see infrared energy, infrared wavelengths, so they can see in the dark. Okay, we will see why this is very important immediately here. Looking at the spectrum of electromagnetic radiation, we will see the broader spectrum in a minute. Electromagnetic radiation ranges from radio waves with wavelengths of hundreds of meters or more. So that's really what is used for transmitting radio signals, to gamma rays which have wavelengths of 10 to the minus 12 meter, which is as small as the size of an atomic nucleus. So remember, we said short wavelength means high energy, so the gamma rays have a lot of energy, like X-rays as well. So you can see here we are going from gamma rays 0.001 nanometers to X-rays to ultraviolet, which a lot of it is getting trapped in the stratosphere because the blue ultraviolet light, which has high energy, is bombarding the oxygen molecules and splitting them into oxygen atoms, and oxygen atom is then combining with an oxygen molecule to form ozone. So fortunately for us, all the high energy blue UV is absorbed in the stratosphere. Why? Because if that comes into the troposphere where we live, it will damage the DNA. This is why we worry about ozone hole, for example. Okay, and then you have infrared. We will see a little bit more later on. Radar, TV, FM. So radio waves are in this range here, out to AM, which are at wavelength of 100 meters. So Earth is emitting in this range, and we will see here that most of the energy coming into the atmosphere is visible spectrum, which goes from 300 and some nanometers to 800 and 700 and some nanometers. So life has evolved. Photosynthesis was, for example, has evolved to use light in this band. We have evolved to see in this band, and so on and so forth over time. Okay, so what is it good for? Essentially, any molecule that has what is called a dipole moment. So if you take opposite signed charges, remember molecules, atoms have neutrons and protons, and if you have charges separated, then they develop what is called a dipole moment, which makes them, let's say, conductive, interact with electromagnetic radiation. And what does that do? As the energy increases, you can have the electronic states of any particular atom or molecule at ground state, and you have excited vibrational levels. And if you bombard it with photons of energy, either coming from the sun or going out from the Earth's surface back towards space, then you can move that atom into a first electronic excited state. If you have more energy, you can move it into a second electronic excited state. If it loses that photon of energy, then it can fall down here, and if it loses one more, it can fall down here. So here we are IR, which doesn't do much for many of the gases and molecules and so on. Visible can have energy that excites many substances, molecules, atoms into first electronic excited state, and UV, which we mentioned, blue UV, which has high energy, can put many things in the second electronic excited state. Okay, so it becomes clearer here. Interactions of electromagnetic radiation with molecules. In the top we saw absorption of a high energy photon with an ultraviolet or visible wavelength can lead to excited electronic states. So basically, when you bombard an atom, if it can absorb energy at that wavelength, at visible or at UV, then its electronic state is excited, which means it begins to have kinetic energy, which we will see in a minute becomes temperature. Okay, so each excited electronic energy state has substates with different vibrational levels. Absorption of a lower energy infrared photon can excite a vibrational level without changing the electronic state, so you can remain in the ground state and still absorb energy. In the bottom we are looking at absorption of low energy photons at microwave or infrared wavelengths can lead to rotation or vibration of molecules, whereas high energy photons at ultraviolet rays can break apart molecules. So high UV here, let's say this is oxygen. Oxygen can be bombarded by UV and be split into two atoms. Then, as I said, the atom can combine with oxygen molecules to form ozone. So here we are going from higher energy, shorter wavelengths, to longer wavelengths or lower energy. Visible is somewhere here, so IR is creating excitement, but it's not changing the state, whereas microwave here is bombarding and creating molecular rotation, here molecular vibration. So if it doesn't make complete sense, don't worry about it. These are the kind of details that are needed for understanding how the energy from the sun is being absorbed, how it is being distributed, and how it is being sent back to space, because we have input, we have output, and we are trying to understand the equilibrium. Why? Because we are now actively perturbing the equilibrium by putting energy or greenhouse gases by burning fossil fuels, and we'll see how that works. This is kind of the very basic we need for understanding the theory of climate. Okay, so we'll leave it here, but we'll keep adding more details with energy balance and so on. Then things become clearer and clearer as we go along.